Hi, everyone. Thanks for having me, and I'm delighted by this opportunity to share our recent research about democratizing LLM training by exploiting low-rank gradient. I hope that could be of interest to this audience who are interested in decentralizing AI. Let's start it by something everybody knows now. Large language models are so powerful. They help us do conversations, generate plausible content, do a form AI agent, do complicated reasoning, and even sophisticated planning tasks. But same well-known as their capability, everybody also knows training or even fine-tuning the best large language models is extraordinarily expensive and beyond most, if not almost everybody's resource availability. That comes with multiple bottlenecks. Training the best large language models need the highest end GPUs that cost money. And even the best GPUs will take days or months to train, and not to mention about the data and the human resource you need to pay for that efforts. So people sometimes say, very soon training language model will not only be beyond the individual's reach, but even beyond the reach of even small countries' budget. Our vision is to democratize the training of LLMs. We ask the question, beyond using the highest end GPUs, is it possible to democratize LLM training with those cheaper ones, those consumer grade GPUs, not those expensive ones in the data center, but those available in your computer or even someday in your mobile phone? So we took a look at comparing between those good GPUs, those top-end GPUs such as H100, A100, those most popular in data centers, and the consumer-grade GPUs. For example, the 4090 is a good GPU for gaming purpose, and you can often find it in good desktops. So comparing their specifics, we find that they are actually not too far away in terms of compute ability. For example, you can look at the FP16 compute performance between A100 and 4090. They are not too far away from each other. But the biggest difference lies in their memory and communication, which is necessary because nowadays LLM training involves massive dataset and huge storage for model parameters, gradients, and other training artifacts. So when you see such a big price difference between the high-end GPUs of H/A100 versus consumer-grade GPUs, those 10, 20, or even hundreds times of differences, those are where you pay your money. You pay the money for GPU memory and communication, not necessarily for compute power. So looking at this limit, we realize that contradicts. So this seems to contradict with the current trend. If you talk to any LLM researcher, many will tell you scaling is all you need. That is, keep increasing model size will solve most of our research problems naturally. This is a topic on the debate, but there is no denying that it has become the common practice of most industry companies leading LLM research nowadays. So is there any chance that can save us from keep scaling the model while keeping the GPU memory war? Is there any chance we could use those consumer-grade GPUs while scaling keeps to dominate? And our answer is there is a chance to mitigate between the two. You could keep enjoy your big model as long as you keep your gradient small, because it's the model and the gradient constitute the major training memory cost. So if you can reduce gradient, you can save more size for model scaling. Is that possible? Technically, it turns out yes, by discovering one fact, that is the inherent low rank phenomenon in LM gradients. When we talk about low rank, let's start from some arguably most familiar method regarding low ranking LM called low rank adaptation, or LoRA. It is a parameter efficient fine-tuning method. Given a pre-trained large language model such as Llama 7B, it will fine-tune the language model to fit a downstream domain by assuming the fine-tuned weight equal the summation of the original pre-trained weight and a weight delta. And this weight delta could be represented by a low-rank factorized format. And this low-rank factorization will save much space compared to the original dimension of the weight. And that's where LoRA could save you lots of memory. LoRA could have or become the de facto method in fine-tuning, but with certain caveats. Number one, LoRA could only fine-tune the model. It cannot pre-train a model from scratch. And number two, LoRA is a kind of ad hoc solution by assuming the weight delta to be low rank. It also changes the original optimization objective. So that motivates us to go beyond the LoRA and develop a new method called gradient low rank projection, or Gallo. Gallo is capable to save memory for both pre-training from scratch and fine-tuning. For the first time, it is able to reduce the pre-training memory cost of a Llama 7B model under 24 gigabit. That is below the memory of RTX 4090, a good custom consumer-grade GPU, which is encouraging for the first time. And by third-party evaluation, in fine-tuning cases, we also outperform other existing solvers, such as 8-bit quantized LLM by using less than half of its memory and a higher token throughput and comparable or better result. So let's look at what Gallo does. It's a very simple algorithm, in fact. We have 3 steps. First, compute the gradient in the original space, and then project that into a low-rank space using the SVD of the past gradient, or in fact, other low-rank projectors are possible. So we usually choose the rank to be very slow, so the projected gradient is much smaller in size compared to the original. We do the update in this projected space, and after that, the update is projected back into the weight space and update the weight. So in this way, we are saving the grid. We are saving the optimization state and the projection weight, the optimization state from original full ranks 2MN into 2NR. Remember here, R is our rank. So compared to the original M, it could be thousands of times smaller. That's where the memory saving comes. With this simple 3-step recipe, project a gradient, updating projected space, and projected back. Gallo is compatible with all the mainstream deep learning optimizers, such as Adam or AdamW, because they could just be plugged in to be used in this projected space. Also, beyond an ad hoc method, Gallo is a provable method, and in our paper, we show that the gradient will be provably low rank. For large transformers, the weight trajectory is guaranteed to move in a few low-rank subspaces along the training, so it becomes principled. In pre-training, Gallo can pre-train a Llama 7B model with a token batch size of 256 on a single device, without active checkpointing and memory offloading. So that enables training Llama 7B on RTX 4090 for the first time. Also, we cite another third-party report on fine-tuning result. So people fine-tuned the Llama 7B model on the same consumer GPU 4090 with a 70 gigabit VRAM, and they found the loss curve dynamics to be almost identical with the full training, showing that Gallo is able to recover the full training dynamics. And that's also manifested in the close performance between Gallo's fine-tuning result versus the full tuning result. And remember, the full tuning result is thousands of times more expensive in memory compared to Gallo. And then compared to another method, the common method, LoRA, Gallo consistently perform on par or better. And because it's an attractive trade-off between memory and performance, Gallo has been popular in the open source community and implemented by leading open source libraries, including Hugging Face, PyTorch, and Llama Factory. Even further, our recent method has integrated Gallo with quantization. That is motivated by the observation that popular laptop GPUs, such as RTX 4060, are equipped with up to 16 gigabit of memory. So we set 16 gigabit memory as our next goal up to 24 gigabit. And we reach our goal by carefully study how to quantize each part of Gallo algorithm. We found that some part of Gallo algorithm, such as the projection step, can be deeply quantized without affecting the performance. And by reducing the memory cost further from 24 to 16 gigabit, We can fit the pre-training of Llama 7B into 4060 Ti, and that will reduce the price further by more than 3 times based on the price as of August 2023 in GPU hardware. And Gallo has this new algorithm we call Q-Gallo has further pushed the boundary of memory performance trade-off. At the pre-training stage, our new algorithm facilitated training a 7B model from scratch on a single 4060 Ti with only 16 gigabit memory. At fine-tuning, it reduced memory consumption also by 50% compared to LoRA and Gallo, while consistently outperforming Q-LoRA, another quantized fine-tuning solution by a large margin at the same memory cost. With that, I hope to share you with our vision that in one day, everybody should be able to train their own language models with their own GPUs, however many and wherever they are. And I would like to attribute the thanks to my collaborators, and thank you for your attention. Bye.